Dr. Sharma, I've given another number.
Okay, Mridita madam, over to you. We are live now.
All right.
Yes, sir. I received your number.
All right, all right. In
Fine.
case of any emergency, you can call me.
Yeah, yes. Okay.
Okay. So, a very good morning to one and all present over here. I would like to give warm welcome to our today's guest speaker, Dr. Snehal K. Joshi, Vice Chancellor Dr. Shailendra Sharma, Dean Engineering Dr. Pradeep Lashkar, Head of the Department of CSA Dr. Nilesh Jain, In charge Triple I Cell Dr. Balkrishna Sharma, all the dignitaries, HOIs, HODs, Mandsaur University, Mandsaur. As today, Department of Computer Science and Application, Mandsaur University is organizing an online webinar on image classification using convolutional neural network CNN. For this workshop, our guest and keynote speaker, Dr. Snehal K. Joshi, is with us. Dr. Joshi have completed his master in information technology IT from Manipal University, Karnataka, and he have done his PhD from JJT University, Jhunjhunu, Rajasthan. The main area of his research involves medical image processing. Dr. Joshi has 9 plus years of experience of corporate and 20 plus years of experience in academics and other area. He have published 9 books as a solo author and around 12 research papers in the academic journey. Currently, he is a Dean of Computer Science and Information Technology faculty, Veer Narmada South Gujarat University, Surat, and he is head of the Department of Computer Science at Dalot Usha Institute of Applied Sciences, Valsad. On behalf of Department of Computer Science and Application, Mandsaur University, I would like to give a warm welcome to you, sir, and I just want to hand over this virtual mic to you. Over to Joshi, sir. Thank you.
Thank you very much for your generous words, and I'm really grateful to the host, University Mandsaur University, Dr. Sharma, and all other dignitaries. My topic is image classification using convolution neural network. And since topic is related with convolution neural network, I guess that all the participants are very much clear about the neural network concepts. Although we will cover certain portion related to neural network here, but we'll mainly focus on image processing using convolution neural network. We will also work on one practical aspect, and we will talk on practical uh, execution of one program using Jupyter Notebook. So let us understand what do you mean by machine learning and deep learning, and these are on a very primary level definition or concepts related to ML and DL. ML stands for machine learning, and DL stands for deep learning. Basically, deep learning is a subset of machine learning, and it is used mainly in artificial intelligence that has networks capable of learning unsupervised form. So basically, you know understand that what is supervised and what is unsupervised. For example, if somebody is guiding you to understand or to classify the things, okay, that is what the supervised learning. And in certain cases when you are independently doing it at your own, that means you are distinguishing based on your own learning, that is unsupervised. supervised and unsupervised are two things, and like all the kind of classifications, clusterings, and other things, they are based on either of these kind of algorithms. Which one is better, whether it's a supervised one is a better or unsupervised one is a better, depend on problem. So which kind of problem you are working on. So it depend on that, that which kind of algorithm you are going to select, whether it will be a supervised or unsupervised. Mainly machine learning programs are used when you have number of known features to you. So if you have large number of feature sets with you, now what do you mean by feature set? Okay, for example, suppose you want to talk about the customers of bank. So bank customer related information contain customer ID, customer name, from which city he is from, what kind of work he is having, that is a profession, what is his salary, what is total bank balance right now, how many FDs he has taken. So these are all features related with particular customer. So if you have large number of data set related with the customers, okay, in this particular example, then these feature sets can be used to predict something, to classify something, to cluster something. That is a feature set. Similarly, so assume that you are working on different flowers. You want to distinguish between different kind of trees or flowers or animals or something. So if you have their known features, that means what is the length of the petals, what is the width of the petals, what is the color and shadow of the petal, etc. So all these known features are with you, and the larger number of features you have, it is more easy and more better way you can perform and develop a good machine learning ML based model that can work efficiently. But in certain cases when it is very difficult to classify or have the feature sets, for example, like we will go through certain examples here. In classification, image classification problems, basically image doesn't contain numeric or categorical data, because images are images, the one you can just view them, okay, it doesn't contain any kind of numeric or categorical data. And images contain features, patterns, and hidden data. So extractions of these features, and like after by extracting the features, classification based on similarities of features and differences among them can be used. Image classification problems are basically based on both ways, supervised and unsupervised, and or semi-supervised. Okay. Now, what do you mean by computer vision? That is another word. It is known as a computer vision. What do you mean by computer vision? So, computer vision is a field of artificial intelligence that train computer to interpret and understand the visual world. So whatever you see, it understand, it train itself and distinguish itself. Okay, particularly in robotics and robot arms, or even in case of various avionics, various industries where you are using different robotics, IoT based applications. So it learn it its own, right? Like traffic controlling, auto traffic controlling, signal handling, then vehicle identifications, etc. So all these things are basically related with the computer vision problems. So it involves methods of acquiring, processing, analyzing, and understanding the digital images and extraction of data from the real world to produce information. Now, next is basically we'll talk about how to perform these actions. So for this purpose, we have certain important things which you use for this purpose. And so these are very rich libraries that we use. Okay. So one of them is a PyTorch, another is a TensorFlow. So if you want to work on convolution, like convolution neural networks, CNN based problems, or computer vision problems, these are very efficient tools that you can use, and it will give you a good result. Like PyTorch is one of the very prominent, and like it's an open source machine learning library. Second is a TensorFlow. It is very useful library that contain end to end open source platform for machine learning. And similarly, keras is a very rich library. It's an open source one, and it basically work on over the TensorFlow. And on top of TensorFlow you can use it, and it is very efficient for deep learning and neural network based problems, suitable for fast experimentation. And you need CPU. Like normally we work on GPUs as far as image processings are concerned, right? Because it need a lot of processing. All right. Now look at this particular example. Here you have different images of different birds, and these birds, although they are birds, their class is bird, they are coming from the same class, that is bird, but each of them are different. And what makes them different? How they are different from each other? So if you look at them, okay, they have different colors, different size, different eyes, okay, different shadow. Okay, so these are various features that you can look at them, but like how you will distinguish them? If I tell you that, okay, distinguish them based on the feature, how many features you can work upon? So yeah, tail is there, then they have wings, they have color, they have shadow, they have eye, they have peaks, right? So these are some 8, 9, 10 different features you can extract. That are, but that is not sufficient enough to distinguish what the image contain is lot many features, hidden features with that, right? So these are different images, and just looking at them only you can distinguish that, okay, these are separate different birds because they contain different features. Okay, now look at this cat family. Okay, this, although they are from cat family, but they have different features. All right, like lion and tiger and panther and different puma is there, cat is there. So they have different feature. They have different skin color. They have different facial color. Okay, different nose they have, different shade they have. So these are various features that they carry, they contain. Okay, similarly human faces. So human faces again, they are different, they have contain different, although all of them have a feature. They have nose, they have lips, they have eyes, they have hair, etc. But they have different features because they look different. All right. So these features, there are a lot many features available that distinguish between them, and that we cannot classify and write down and create a table uh, based on that. Okay. Now next is like, who is the person behind this particular convolution neural network? So Yan LeCun, he came up with this idea in 1998, and he is the person behind the concept of CNN, convolution neural network. And this particular, he used the neural network and used the concepts of feature-based distinguishing the images and objects, and that was a basic concept behind this particular this field. CNN gradually developed, and now due to enhancement in hardware and various softwares that we have, various technologies we have, it is very much emerged. Now, how the convolution neural network works? So basically, Yann LeCun, he developed the whole concept based on our neural system, the human neural system. So human neural system is consist of three part. Okay, this is actually a dendroids, and then second part is soma, and the third part is axon. So your neural system is consist of these three things. So here what happen is, like, your dendrites are carrying the signal or the data from terminal button of another neuron and carry to the soma. That soma is the nucleus basically. So nucleus process the data and forward it again through the axons. And axons are the terminals button, or they are known like synapses, which forward it further to next thousands of neurons. So that was the basic concept behind the complete CNN model. So this is exactly how it work here. Like, these are dendroids. They come to soma, which we call it as a node in our neural network. So you have different weights here. They are coming. and the soma is there, that is a node that performs certain action and carry ahead. you know so the neural network is having one input layer, one output layer, and then you have a processing node here. So basically the concept of neural network is like this: you have different nodes available as an input layer, then you have the processing part, that is a hidden layer. So you have multiple layers consist of different number of nodes in each layer. And finally you have output layer. So the hidden layer can be one or more than one in numbers depending on your requirement or application. So suppose like you want to provide a image, so whether a person is smiling or he's a sad or he's a happy or sad, you want to bifurcate them, you want to classify them. So what you need is you need a model, CNN model, and you pass on one image and it give you or classify it and whether he is happy or he is sad. But it is very simple to talk about this, but it is not that simple when you are working on the model. So the model itself, the CNN model, okay, this is what we want to develop, CNN model. And what is the purpose of CNN model? So we want to fit the model in such a way that it give the output with the maximum accuracy, with the highest accuracy. All right, that is the ultimate aim behind the CNN. So with a higher probability, it explain you that yes, this particular image is of this class. All right, as far as the classification problem is concerned. All right. So since you are using images in two ways, either it will be a black and white image or it will be a color image. So if it is a black and white image, then obviously it will be converted into 2D array, two-dimensional array. So the image is converted pixel by pixel in a array of pixels, basically a two-dimensional array, right? So each element is representing particular pixel. All right. Similarly, when we talk about the color image, so color image will have a three layer and it will be a three-dimensional array. So three-dimensional array, it will be like, suppose image is of size m cross n, then we'll have three-dimensional array of m cross n. All right. So each of the dimension is represented by a particular color. So normally we talk about RGB, red, green, blue. All right. So we have so basically an image is converted into uh, array of either two dimension or three dimension. If the image is black and white, it will be converted into 2D. If image is color, it will be converted into 3D. Okay, this is how it is converted. So basically images are converted into layers and features for every pixel are obtained, and this is how you can have uh, array of your image array of pixels represented as zeros and one. Now, building the neural network, how to build that? So basically the neural network works using these three things. Okay, one is a forward propagation, second is a backward propagation, and third is the activation function. So these three terminologies are very important to understand. Okay, we will just talk at very basic level. I will not go much deep into that because we have a lot many things to cover. All right. So forward propagation, backward propagation, and activation functions. These are three things that makes your neural network works properly. Okay, that's a basic thing behind how the neural network work actually. So forward propagation, how it works. Now, in case of forward propagation, what happen is you have two inputs, input neuron like say x1 and x2. These are two input neurons. Okay, and when it process, so each of them have their own weights. Okay, so x1 and x2, these are two input node. Okay, they carry the input value, but each of them have their own weights. Okay, so weights are represented by W1 and W2. And what do you mean by weight and why you require weight? We'll understand that in our next slide. Then there is certain bias as well. Okay, so basically when it process, it will be x1 dot w1 plus x2 dot w2 plus b1. So based on that, it will calculate, and that will be your processing part. Okay, and this will pass next to the activation function, and activation function will be applied on that. Okay, so basically what forward propagation do, for example, if you want to create a pink color, you want to develop a pink color, so how you will create a pink color? So this is your process, pink color. Okay, but it is consist of x1 plus x2, but it is not pure x1 and x2. Okay, it is not just red and white. What you do is you add 80% of red and 20% of white. So 80% is a weight W1 and 20% is a W2. So basically x1 dot W1 plus x2 dot W2. Then plus B1, that is your bias. What do you mean by bias? So it is not just pure color 80% and 20%. There are certain environmental things, like humidity is there, temperature is there. These are certain features which are beyond your control, and they are also included when you create the color. So that is known as a bias. Okay, so bias is certain element that affect your that affect your forward propagation basically. So that is what you call as a bias. So that is what the weight and biases are basically. Okay, with this example, it will be very clear to you that how it works. Okay, now let us understand and build the. So that was about forward propagation. This is how it work, and forward propagation go ahead. So in one direction, but it is not just in one direction. Okay, what happen is after forward propagation, it improve its weight also, because we need a color, but this we see that okay, this is not perfect pink color. So what you'll do is you go back. Okay, you will go in backward direction, and then you will adjust your weights and bias heat. Okay, you will try to eliminate the bias, you will try to reduce the bias, as well as you will try to change the weights. Okay, so that is known as a backward processing. So every time, by to get the perfect color, what you will do is you will perform forward propagation, then you will get the result, then again you will perform certain backward propagation, you will change the weights, rectify the bias, again you will perform forward propagation. These things goes on until you get the optimum result. Okay, or the best possible result. So this is how forward backward propagation keeps on. Okay, goes on. Now let us understand the CNN, how it works. So CNN model is basically excuse me, CNN model is basically, you can execute it in 4 steps. So step one is a convolution step, then you have max pooling step, then flattening, and then finally fully connection. Okay, so these are 4 important steps, and this makes your CNN model. All right, so let us understand them one by one: convolution, max pooling, flattening, and fully connection. Okay, for example, we want to build one CNN model, and this is one example. Like we have a data set, and this data set contain training set, testing set, and single prediction. These are 3 things we have. Now, what do you mean by training and testing? So, yes, we want to build the model. So, we will build the model by training it, by providing it some images, okay, that train your model. That means we will inform that, okay, these are this particular image is of cat. This image is another cat. This image is a dog image. This image is of another dog image, etc. This is how we keep on providing the images, different images of different dogs and cats, taken from different angles, with a different background, and this is how we provide to our neural network, our model. Okay, and model will keeps on updating its weights and biases every time it receive the image. It keeps on updating the and extracting the features. It extract the feature, it update itself, it explain itself, and this is how the model is learning. So that's the learning phase of your, and we call it as a training. Okay, so training. So for training purpose, assume that we have, like in this particular example with that I'm explaining right now. We have taken a total 8,000 images of dogs and cats for the purpose of training. Okay, and once you develop the training model, once you train the model, then we would like to test our model, that whether our model is perfectly classifying them the image as a cat or dog, or it is not able to classify them. Okay, so that is our testing phase. So for testing purpose, we have taken 2,000 images. All right. So we have 8,000 images for the purpose of training and 2,000 images for the purpose of testing. And then finally, like we will keep certain images with us, and we will finally, test them for the purpose of prediction. So this is what we are doing. Okay. And this particular data set is I have kept in my, Google Drive, and I have these three folders: training set folder, testing set folder, and single predictions. So this is what I have. All right. Now let us understand the code, that how it work. Okay. So we need certain, libraries. So we will just add them. So here we are adding certain, libraries and modules that we are going to use. We are not going much detail into this, but we need certain modules and libraries and that we are including here. Okay, that's fine. Now this particular code I have written using Python. Okay, and using TensorFlow and Keras libraries. Okay, they are important one. Next is what we do is like we will import the data set. So like data set, since I, as I told you, like it is available in my Google Drive, so I have to mount the Google Drive first of all. So I'm mounting it, then just checking it. Okay. And then next is like we will import Keras library and important classes of convolution. So these are certain important classes: sequential, convolution 2D, convolution, because we are using convolution 2D module. The reason is class. The reason is this class is this particular example is related with image process. It's a two-dimensional image. If you are using three-dimensional image, that means a video streaming and all. So for that purpose, we have to use convolution 3D class. Okay, con 3D, it is known as con 3D class. Then you are using max pooling, flattening, and then these are different classes that we are going to use for this particular example. Next is augmentation and training the database. Okay, now what do you mean by augmentation and training the database? Augmentation is one of the important feature. One like what you do is when you get the image. Okay, so you need to augment the image. So augmentation of image is you are changing the augmentation of the image, like by shearing it, by zooming it, by like vertical flipping, horizontal flipping, etc. So you are generating a number of different images from the particular image. So here what you do is one image, if it is a straight image given to you, if it is tilted, if it is zoom, if it is flipped, okay, and still you need to train your model uh, on the same image but with different augmentation. For this purpose we use augmentation. Okay, and augmentation is very important part. So for the training test, training data set, we are augmenting them. For testing we will keep as it is. Testing images we will not augment them. Okay, so next is we will rescale also, because rescaling is also important. We will not we need to rescale the image because we want to make it uniform. All right, because images will be of different type. Okay, some of them might be say 512 by 512, some of them are of 1024 by something. Okay, so we want to bring all the images of the same shape and same size, so we need to rescale them as well. Okay, that is very important. Next is like setting path for our training and testing data set. So our data set is available in two different folders. So we create a training set and test set. Do these two different path we are setting, and for that purpose we pass the path. We pass the target size. So our image is of 256 by 256. And then we'll provide a batch size. So batch size is like when we will train the model, we will pass 64 the images in a batch. So suppose I have say 8,000 images with me, then every time I'll pass one by one 64 images. After passing them, my like after passing them one by one, a model will be trained, and then after this particular batch it will back propagate. That means it will update its weight. Okay, so that is what the batch size. So batch size specify that after how many images your back propagation work. Okay, so that is what we do. And then class mode we need to specify here. Since this is a classification problem, so it will be a binary class mode. The reason is that either it is cat or dog, so we call it as 0 and 1. So it's a binary kind of classification. So binary class mode will specify binary. So in short, what we do is next we just set the path. So what we did again, let us understand. First, we have these images. First, we import all the classes. Second, like we augment the images. Okay, and we have two separate training and testing data sets. Suppose we have single set, then we have to divide them into training and testing. Here I have already prepared. It's a pre-prepared uh, folders with me for the purpose of training and testing. Next is rescaling. So you need to rescale it, and finally, like we set the path for training and testing data set. Okay, now this is what we are going to perform. So yeah, our training and testing is done. Now first step is the convolution step. So we need to understand now what we'll do with our images. So first part is the convolution part. In convolution part, what we do is I have one image. Okay, assume that this is my input image. Okay, and this input image is every pixel is converted into contain a specific you know it's a binary number. Okay, assume that it is represented as 0 and 1. Okay, as such in our original image it won't be like this. All right, just for understanding I'm giving you this particular example. Okay, so like your input image is like this like for example, what you do is you use feature detector. So you use different feature detectors. Okay, that is known as a feature mapping, and these feature maps are of different size. Normally, it is used 3x3 feature map, or 5x5 or 7x7. Even 1x1 is also sometimes used, but it is not advisable. Uh, Ideally, 3x3 or 5x5 are used feature detectors. These feature detectors, what they do is they stride over this particular input image. So striding means like it's a 3x3. It will start with the first 3x3 image part, and it perform the like it perform like your matrix multiplication. And how it do, like okay, so it will just multiply 0 into 0 plus corresponding position, it will multiply and add them. Okay, so it will be a sigma of corresponding positions multiplication. Okay, sum of corresponding positions multiplication of two matrix. So this feature detectors stride over it. Okay, so first of all it is here, then from the second column, then from third column. So it perform this action, and for every action it convert, and whatever result you receive will be keep over here. All right, so you'll have result here. It is known as a feature map. So basically you have input image, you are performing using a feature detector, stack of feature detector, and that generate feature map. Okay, so basically purpose is that we are extracting the important features from the images and reducing the size of the image. It is known as a dimensional reduction. Okay, so dimensionality reduction process is done over here using the feature detector. Plus we are using different feature detectors. It is not just single feature detector, it is purely an intuitive process, and you use normally 32 or 64 or 128 different feature detectors, and with every feature detector it generate a feature map. So if you are using 64 feature detectors, it will generate 64 feature maps for a particular image. Okay, so for every image you are generating different feature maps, and that is extracting the basic fundamental like basic features of that particular images. All right, so this is how it perform. Now next is like as I told you that from input image what you did is you are obtaining the feature maps, a stack of feature maps. Okay, and this particular process is known like it will give you final feature maps, and this particular process is your convolution layer. It generate a convolution layer. Okay, so convolution layer is basically applying feature detector on the input image that give you feature maps, a stack of feature maps, okay, which possess the important features of the input image as well as the dimensional reduction of input image. So that is the basic purpose behind your convolution layers. All right. Next is ReLU layer. Now, after obtaining the convolution layer, next is we are using activation function. So activation function is actually it give limit your feature maps into a particular range. Okay, and this particular activation function where there are various activation functions available with us. Purpose of activation function is that okay, when you perform like when you are learning your algorithm is learning, okay, that is a process that is known as like when you perform back propagation and all. So it's a learning process, and there exists a problem. Okay, and this particular problem what happen is that after certain processes it stop learning further. Okay, because learning rate will become too low and all. Okay, similarly another way is like you want a result in particular range. Okay, so for that purpose also we are using activation functions. So here we are using activation function. Here we are using the rectifier, that is a ReLU rectifier. Okay, and ReLU is one of the activation function that we are using. Okay, and on your feature map we apply the ReLU activation function. So you have a ReLU layer, okay, that you get ultimately. So the first convolution part is consists of three things: input image, you apply your feature detector and get feature map, and feature maps are they are passed through the activation function, and you are obtaining the final feature map. Okay, so that is the step one. So first of all, what you'll do is CNN equal to sequential, since our classifier object using sequential class. Okay, so we will have this. Okay, in this particular problem, we are using 64 feature detector of size 3 cross 3, and like here we take it as a 256 by 256 color image. So we have three channels. All right, and we add our first layer. So first layer contains 64 feature detector, and 3 cross 3 will be your feature detector size. Input shape of image is 256 by 256 with three layers because it is RGB color image, and activation function we are using is ReLU. So we have this first layer, that is a convolution layer. It is created. All right. Now next step is after convolution layer. Okay, what you'll do is you'll pull the important features from these convolution layers. Okay, so that is a pulling step. In pulling step, what you do is like these are all images of cheetah. Okay, but cheetah is having features, different features, and they are this picture. All the pictures are different from each other. Okay, from taken from different angles. Okay, similarly, these are various pictures taken. I mean, converted. The same picture is converted using augmentation. So you have augmented the image. Now from these different images of the same animal, what you do is you are extracting the features from that. That is known as the pulling part. Okay, so you have three kinds of pulling. One is a max pulling, second is a mean pulling, that is a minimum pulling, and third is the average pulling. So out of them you can use a particular pooling. Okay. Now here what you do is like we are using max pooling. The pooling size is normally given for this particular example. Say for like pooling is like 2 cross 2 pooling. So what it'll do is like it will it will stride over the feature map. Okay, one by one, and it will obtain the maximum pooling. It will obtain the maximum number, okay, or maximum feature, okay, from this. For example, you look at this for first 2 cross 2. So here, which one is the what is the maximum value? Which is the max feature? It is 1. So you are getting 1 here. Okay, similarly it's tied over. So now the second column and third column and first row and I mean second column, third column, first row and second row. So in this, what is the maximum feature available? That is 1. So it is again get 1 over here. Then again it will slide over. So now you'll have third column and fourth column and first 2 rows. This is how it pass through all the rows and columns, stride it over, and finally you are getting the pooled feature map. So from feature map you are getting pooled feature map for every feature map. So here again feature map dimensions are reduced, okay, and you are getting pooled feature map. And this particular process is known as the pooling. Pooling is basically related with extracting the important features from the feature map. Okay, so you had original image converted into feature map. Again, feature map is converted into pooled feature map. Okay, which contain only important features. Okay, am I audible properly? Yeah, are you getting me? My voice is clear?
Yes, sir.
Yeah. Yeah. All
It's
right.
clear.
Thank you.
Yes,
All
sir.
right, all right. So for pooling process, okay, what do you do? How you do that? Okay, it's a single line code basically. Okay, so pooling step is actually reducing the size of convoluted image obtained from step one, and it reduce size of feature maps, and therefore it reduce numbers of nodes in flattening step, and it reduce time complexity and high computation as well, because the higher number of features you have, it is or like more computational burden is there. Okay, so that is how you are getting the pooling. Okay, so here like you are using max pooling function with pooling size you are providing, that is 2 cross 2, and you are adding that particular layer as well. So that's a pooling layer you have. Okay, so you had this input image, then you had this convolution layer, and then finally pooling layer. Now this pooling layer is each of the pooling layer is converted each of the pooling layer is converted into a flattening layer. Okay, so flattening is what? Like suppose this pooling okay, you have this pooling set here, pooling layer, you have this feature map, and then you have pooling map. Okay, so pooling map contain stack of different pool images you have, and assume that it is 4 cross 4. Assume that it is 4 cross 4. So how many nodes are possible? 4 cross 4, 4 into 4, that is 16. So you'll have 16 nodes here. Okay, so basically from 2 dimension it is converted into a single dimension. Okay, so that is known as flattening of it. Okay, so flattening is basically it is converting into vectors. Okay, from array to vector, you are converting it from array to vector, and that is what the flattening is. So number of features you have in pooling layer, okay, in like pooled map, okay, that will be your input layer for neural network. Okay, that will be your input layer for okay, so this is how your input layer of feature ANN will be there. Okay, now next is your flattening. So flattening is the process of generating input vector from pool feature. So you have this pool feature map and convert it into flattening. So say it is 3 cross 3, so you'll have 9 nodes here, right? This is how it is converting into pool feature map is converting into your flattening. So it create a vector of vectors containing, so like this pool, as I told you that pooled pulled layer contain number of pulling images. Okay, so every pulled map is converted into flattening. So you have vector of vectors. Okay, so it's a multi-dimensional vector you have. Okay, multi-dimensional in the sense a stack of vector you have. Okay, so it create vector of vectors containing feature maps, and that is known as a tensor. We call it as a tensor. So this stack of vectors or tensor will be an input to the neural network. Okay, so like this will pass value to the first node, this will pass to the second node, third node, fourth node of the input nodes of neural network. Okay, now flattening, it flatten every pull feature map and make a stack of vector. And one feature map is represented by one input layer consisting of nodes. So you have pulling layer and flattening, and finally you have input layer of feature ANN. Okay. Now, next is you have flattening part. So how to code it? Simple, add and then flatten. So flatten is a function, and you simply add it. So flatten function generate tensors, and it is added as a third sequence to the CNN. Okay, classifier CNN. Now, important part is your full connection. That is your neural network. So full connection, like how many nodes at input layer, how many hidden layer, and how many how output layer. So we don't need to define how many input layers because it depend on your flattening layer. Okay, number of elements available in your vector. Okay, that much number of nodes will be available at your input layer. Okay, now so you have your input layer, it is passing to the hidden layer, and then like number of hidden layer you have to decide, and then finally output layer. So output layer will contain single node. So single node because it is a binary classification. You are just you are just classifying whether it's a cat or dog. Okay, so hidden layer, for hidden layer, like we will keep one hidden layer with 128 nodes, and output layer we will keep a single node output layer because we need a binary type of output. So fully connection, first we will add hidden layer here. First hidden layer, like we use dance function for that. So dance function, we are passing output dimension. So that means it will contain 128 nodes, and activation function we are using is just a minute. Right? Yeah, am I audible? Am I audible? Can you hear me?
Yes, sir.
Okay,
Yes.
thank you. Okay,
Yes, yes.
so yeah, all right. So we are adding this hidden layer here with 128 nodes. Then you'll have output layer. So output layer will contain one node and with activation function sigmoid. So for hidden layer, we are using the loose activation function, and for output, we are using sigmoid activation function. Okay. And then finally, like let us compile the particular model, CNN model. And for this, we are using optimizer, that is Adam, and our cross entropy, that will be our binary cross entropy. And finally, performance measure will be accuracy and mean square error. Okay, that will be what that is what we are going to check. That will be our performance measurement for our model. Okay, so accuracy will use, and we'll use MSE, mean square error, but we'll use other features as well. Okay, so finally we'll compile it, and at the time of compilation we'll provide our optimizer. Okay, basically optimizer is a like used to control the problem of gradient descent, and for that purpose we have different optimizers, but we are using Atom as a optimizer for this particular problem. Okay, similarly, like it produce binary output, so hence we have binary cross entropy as a loss function. And since it is categorical, we can use categorical cross entropy also if it is multi-class classification. And matrix we'll use will be accuracy or MSE. Okay, now after compilation, what we'll do is finally we'll fit the model. Okay, so we'll fit the model, and for that we will provide number of images So here, what you'll do is you'll train the images. Suppose we have 8,000 images, okay, for the purpose of training, mix of cat and dog. So these 8,000 images we will provide once, then second time, third time, fourth time. So every time you provide this, one cycle of 8,000 images will be known as a epoch, one epoch. Okay. So we will provide, we have to fix how many epoch or how many cycle we have to run for to train our model using the same images. Okay. So samples per epoch is 8,000 because we have 8,000 images collectively for the purpose of training, and number of epochs we have given 25, depending on your problem and depending on the trend of your model development. You will decide that how many epochs are required. Normally you can start from 10 epoch to 25 epoch and 50 epoch, and if by increasing number of epoch it doesn't make any difference to your model accuracy or results and loss, okay, then you can stop there. Okay, so number of epochs you have to decide. Then validation data will be like how you will validate your model. So by using test set, because we already generated train set and test set. Train set we are using for the purpose of training. Test set we will use for the validation. And number of validation samples will be 200. So when we validate it, so every time it will pass to a batch of 200 images for the purpose of validation. Okay, so this is how you feed the model finally. And when you execute this, okay, so it will take time, okay, because it will train it. So you are passing images, you are passing the images, input images, 8,000 images in batches. Okay, so since you have 8,000 images and you have kept 64 images, a bunch of 64 images in one pass, so you will have 25 steps for every epoch. Okay, so after every epoch, you'll understand that what is your training accuracy, what is your mean square error for that, and what is your validation loss and validation accuracy. From this you will come to know that how well your model is working and training properly, whether it is in proper direction or not. And look at the output after every epoch. Okay, if you look at here, at first epoch you had accuracy, training accuracy was 0.5790, that means 57.90%. That means at first epoch only your model was able to detect whether it is cat or dog with 57.90% accuracy. Okay, and validation accuracy was 64.39. And gradually with every epoch it goes on increasing. You can see that after 12th epoch it goes to 71.38%. Okay, and finally at the end of 25th epoch you can see that your model is able to classify with accuracy of almost 75%. Okay, so that means out of every four images, three images are correctly classified by your model. Okay, this is very basic model. You can use this performance analysis also. You can see that after every epoch, this is how your training accuracy and validation accuracy is working. Training accuracy is shown in blue line and validation accuracy in red line. Okay, now this is showing your mean square error, so you have red and blue here. Okay, and finally like prediction you can perform. So you will pass the prediction images, unknown images to that, and we identify whether it is working properly or not. Okay, so this is how we can develop a simple CNN model. Okay, these are the steps that we learn, okay, how to classify them. Okay, now you need to understand one more thing, that since we are passing the images, right, and we need output, so output will not be like it will not display that this is cat and this is dog. Output will be in binary, so they you'll have 0 and 1. So what you need to do is you have to label your images. Okay, so you have to label them. So when you train them at the same time you can label them. And labels are like auto labels, basically alphabetically it do that. So C, cat come before D, that is dog in alphabet, so C will be assigned 0 and dog will be assigned 1. So when you get output as 0 or 1, you can identify whether it is cat or dog. Okay, So labeling is also important part. Now once your model is done, it is developed, so performance tuning is the next part. So two ways to improve the tuning: by adding extra convolution layer, so you can have more convolution layer initially, or changing the pooling, changing the activation functions, or by changing optimizers, loss functions. These are various things that you can tune at your model level. All right. So that is what you require. Second thing is like you need to augment your images more. You need more. The more training set you have, better result you can obtain. Similarly, you can improve your hidden layers as well. You can add more hidden layers and all, right? And this is how you can work. Okay. The second problem is your medical image processing and chest X-ray, but like this is related with the classification of chest X-ray. We'll not talk on this. We'll talk on one more problem, and that I want to explain you, practically as well. This is satellite image of satellite images, and that bifurcate whether it is merchant sheep, or whether it is sheep or not sheep. Okay, and similarly, after classifying it as a sheep or no sheep, it will identify whether it is a merchant sheep or a war sheep. Okay, so that is another problem of classification here. But yeah, this is what we are going to talk and execute actually on Jupiter. I'll just explain you the this particular problem, and then we execute. I'll show you how to execute the problem. Okay, so here what you have is like medical image processing of different images. This is a skin image. Okay, skin image taken, simple skin image taken. It is not X-ray image. It's a simple skin image, and these particular spots, they are either cancerous, or they are malignant or non-malignant. Okay, so skin cancer detection, okay, that we are working on a classifier to detect whether the image which you input is a malignant type or non-malignant type, so that you can, otherwise what you have to do is you have to medically test it. Okay, it take a lot of time. You have to take its biopsy, and then you have to perform certain things and all, but this particular model can classify it. So let us see how well our model classify that. Okay, so here the first three images, first row, okay, first row, top three images, they are benign type. Benign means it is non-cancerous, and the bottom three are malignant type. They are cancerous one. Okay, so visible classification can be like visibly you can classify that whether it is cancerous or not. Okay, the experts or doctors, they can suspect that okay, this may be a malignant one. Okay, basic depending on the size and depending on the shade and all. But with accuracy and properly, if you want to perform this action, okay, we need a proper model for this purpose. So this particular classification problem of skin cancer, we have a data set. So we I'm using open data source available from ISIC, and quality dermoscopic images of skin lesions are available in .jpg format, and the size are uniform size. They are converted into uniform size of 224 by 224 pixels, and total clinically verified samples are 3297 images, total images. Okay, out of which 1800 images are benign type, that is non-cancerous, and 1497 images are of malignant type. So total we have this much images available with us, 3297 images. Okay, now we are dividing them into training and testing. So randomly what we did was like we just divided them into training and testing, and we have divided into 70-30% ratio, 70% for training purpose, 30% for the purpose of testing. So here we have 1440 benign type and 1197 images. They are JPG type of 224 cross 224. That is available in our training folder. So training folder contain two folders. One is benign type. It contains 1440 images, and another folder is 1197 images. Okay, it contains 1197 images of malignant time. Similarly, another folder, test folder, it again contain two folders. One is 360 images of benign type. Another one is 300 malignant images. Okay, and major variations are we'll perform dimensionality reductions, then additional convolution layer we'll adding. So here developing single model is not enough. You have to work on different models, you have to work on different approaches, and you have to even use already existing inbuilt models as well, so we can use different models. All right, so in this particular model which I am talking about right now, okay, it contain one like input image will convert into convolution, then we will perform pooling, again we will perform convolution of pooling, again we'll perform one more pooling out of that, and then we'll flatten it. Okay, so this is what the model we are going to use. So here we have two convolution layers, then flattening layer, and then our neural network. Okay, fine. So in this particular model we will talk about is let's check it practically now. Okay, I just want to show you how to execute this. Okay, so here I'm using this Jupyter notebook. Okay, so using Colab, just using this Colab. So Colab you might be aware of. Okay, it is collaboratory provided by Google, and it's available, and where you can execute your code directly. You can use GPUs online, so you don't need to install anything on your machine. And what I'm doing is like I'm simply connecting my Google Drive with this particular collab. Okay, and my data set I have kept in my Google Drive. It is again uploaded, okay, on Google Drive, not on my machine. So any nothing is on my machine. Okay, because when you perform image processing, what you require is a high computational power, and for that purpose you require GPU. And GPU obviously is very costly to have a laptop or machine with GPUs. Okay, so we are using this thing. Even IBM is also providing, and many other, Amazon is providing. So they are providing their own uh, you know uh, facilities where you can execute the codes. All right, fine. Fine. First of all, what we'll do is we'll import our required libraries. Okay. So first step is like we import all our required libraries here. Then next is like we are importing Keras and TensorFlow and other important modules. Okay. And then finally, any other library that we require, we'll do that. Okay. One more thing is that we are uh, we are just providing our input path. My data set is available at in my G Drive, okay, Google Drive, and I have created one skin folder. Again, under that I have a data folder, so I just set the data, okay, and then all required libraries that we are going to use. Next is your next part is like display total images available in train and test sets. So let us by using this code we simply find out how many training and testing images are available in my folder. Okay, so in my training set, benign images are 1440 and malignant images are 1197. And in testing set I have benign images 360 and malignant images are 300. So this is how my image data set is available. Okay, next is we define some constants here. So like our image dimension is 224 by 224, so image dimensions I am providing 224. Epochs, that means number of time we are going to iterate our model for the training purpose. So our model will execute, we want it to iterate and will pass all the images for and train our model for 25 times. So epoch initially I am assigning epoch as 25 value. You can see that if it is improving with every epoch, if your model is improving with the accuracy, you can always increase the epoch number, so that with certain number of epochs you can get better result. Then your batch size. So batch size is what, in like how many images you will provide like in each batch. Okay, suppose we have around say around 3000 images. So like every time we will provide a batch of 64 images. That means after training those 64 images, our model will perform back propagation. That means it will update its weight and biases. Okay, so that is important. Okay, so batch size is very important. A higher number of batch size is less number of back propagation. Okay, lower number of batch size is higher number of back propagation. So it will reduce the speed of training as well. Okay. Next is image augmentation. This is important. So we'll augment the image. Okay. So we'll rescale the image. We will augment it. So that means we'll zoom it. So for that purpose, we are using function image data generator. So we'll rescale it, then we'll zoom the image, and then vertical flip I have provided. For testing, we are just rescaling it. We are not performing any kind of augmentation for testing data set. Now we'll first generate training set. So like directory path is set for train data set, that is image size equal to 24 by 224, batch size is 64. And yes, we are performing this we are generating the training data set. Okay, so here we have given the path, and then target size given, batch size is given, class mode is binary classification, and shuffle we have given. Okay, so shuffling means it will not take image sequentially, it will shuffle the image every time it will train. Okay, otherwise what will happen, it will be a monotonous training, right? So shuffling is very important part. Okay, so we found 2637 images belonging to true class in training set. Okay, similarly test set generate we are generating, and test set contains 660 images total, out of which 360 are benign and 300 is of malignant. Okay, so now test and training sets are done. Next part is now convolution part, right? So now we'll generate, okay, yeah, one more thing, we'll generate test data array also. So that will contain test labels, because we need to generate labels with them. So with benign, we will give a label of 0, and malignant we will give label of 1, so that when we get output, okay, output will be in form of 0 and 1, so we can have exact prediction whether it is, if it is 0 it is benign type, if it is 1 it is malignant type. So we are labeling them, okay, all the data. Fine. Now we will perform this labeling part here. So labeling is done. Okay, fine. Next is after labeling. Okay, next part is yeah, here building the model. Okay, so we will build the model in 5 steps. So first is like we need convolution block. So we'll have 2 convolution blocks here. Okay, and one max and each convolution block will contain each convolution block will contain convolution layer as well as a pooling layer. Okay, followed by another convolution layer and a pooling layer. Okay, and then basically we will perform the flattening part. So like it will be used for to reduce the overfitting, and activation function we are using is relu here. Okay, rectified linear uh, rectifier we are using here. And last layer will be output layer, okay, where we will use sigmoid as our activation function. Okay, because it is a binary classification. And Adam will be our optimizer, and cross entropy is a loss function. Okay, binary cross entropy. Now input. So for input we'll have our 24 by 224 and 3 layer, because it is RGB color type. Okay, so here what you do is, first convolution layer we are making, we are using 16 filters for feature mapping. Okay, each feature map is for size 3 cross 3, so kernel size will be 3 cross 3. Activation function we are using is relu. Padding, we'll have same padding here. Okay, and finally we will pass the image as an input. So input we are passing to the first convolution layer. So that is a image, first image. Now that is image will be your input. Now the first convolution layer will be input for the second convolution layer. So for second convolution layer, again filters we are using is 16, kernel size will be 3 cross 3, activation relu we will use, and padding will be same. Okay, and then we are using the max pool layer. So max pool layer will be, we are performing the pooling part here using max pool, and a pooling size is given 2 cross t 2, so it will generate a pooling layer here. Okay, so a pooling map will be generated for the first block. Similarly, we'll have second block consist of again two we'll have two more layers, and then again we will perform the pooling. So we have two blocks. First block contain two convolution layer, convolution, and followed by pooling. Second block will again contain two convolution and pooling. Okay. Now next is the third part is like you can use third layer also if you want, and okay, otherwise two layers are enough. Here I have used three layers, basically three blocks. Okay, so that is how you can use them. Now next is like fully connected layer. So in fully connected layer, what you'll do is after all this convolution layer followed by a pooling, we will perform the flattening part. So we will perform the flattening. So we are generating vector of vectors, that is tensor we are creating. After that, we have our hidden layer. So we are using three hidden layers here. Okay, so first one is having 256 node, second is having 128 node, and third layer will have 64 nodes. So we are using three hidden layers. Each of them is having varying number of. Normally, this is a tradition. Okay, a good trend, good practice to decrease the number of nodes in like subsequent hidden layers. So the first layer is having 256, second 128, third is 64. Now, obviously, we are using relu as a activation function here. Okay, and next is like finally output layer. So output layer will have like units is one, activation function we are using is sigmoid. Okay, and since the output will be a single node one, because it's a binary classification, it will provide us output as 0 or 1. Finally, we are creating model and compile it. So we just simply compile it. Okay, I'm not executing the codes here. See, it's very simple. I just click here and okay, it is pre-clicked, so it is already executed and results are available. Okay, because it will take time. When I if I click on that, then we have to wait. Okay, for certain period of time. So like I'm just explaining the codes. Okay, uh, this is executed one. Okay, I just executed morning. All right, now finally we create the model and we compile it. So like after compilation, at the time of compilation, we provide optimizer. We are using Adam as an optimizer. Loss function is binary cross entropy, and we will obtain matrix out of that. If you look at the model summary, okay, you will find that, okay, look at this, how many features are available. So in total, you have 32 lakh 67,617 features you have. Okay, how many parameters you are training? Basically, almost 32 lakh 67,000 parameters you are training. Okay, this much features are available. It is extracting. Okay, now imagine, okay, to get this much of features and having it using machine learning. So that is a very very tedious and tough task. Okay, extracting this much. So this is best way to perform. All right, so we are working on different more than 32 lakh 67,000 features. All right, next is we are also offering providing callbacks here. So callbacks are basically it maintain the weights, it store the weight and best possible weights, and also it reduce the if there is any loss, then it reduce it. Okay, and early stopping we are providing. Okay, what is it exactly? I tell you, because when you train your model with after every epoch, okay, you are getting certain result. If the epoch result is not performing better after certain number of epochs, it always store the best possible weights you obtain so far, and that you can store. Okay, that you can use next time when you change the model. Okay, so for that purpose we are storing it. So it is known as a model checkpoint. Okay, and using model checkpoint function we can store that. All right. Next is like here we I am fitting the model finally. Okay, so using the fit command, I'm yeah, fit function. I'm fitting it. So I'm providing training set. Step per epoch is total training set divided by batch size. So it is 64. So total number of images divided by batch size. That will be your like steps per epoch. So here we have uh, like certain number of steps per epoch. I'll explain you. Then total number of epochs we have already given 25. Validation data is your test set, and the validation step will be total number of sample divided by batch size. Okay. So here look at this output. Okay, when we execute this, yeah, this is what the output you are getting, and I'll discuss this output with you. Yeah. So when you execute, it take almost 1 hour or 1.5 hour minimum on GPU. I am using GPU here, okay, on Colab. So these are epochs, okay, and number of epochs are 20. So after 20, I've taken 50 epochs here. After 20 epochs, if you look at this, okay, loss function is 42.62 0.4262. Accuracy we are obtaining is around 78.70%. Okay, that is the testing accuracy, and validation accuracy is around 80.47 after 20 epochs. Okay, I'm using 50 epochs here. Okay, so let's go ahead and check it at the end. So after 50 epochs, you are getting good result, almost training accuracy around 79.75, and validation accuracy around 80.16. So here with every epoch, the we are getting better results. All right. Now, uh, after look at this. Okay, I've generated a plot that compare your model accuracy. So training and validation accuracy is there. Okay, so validation accuracy is here, and it is testing basically. So you can see that okay, it is increasing after around seventh epoch and reaching above 80%. All right, and similarly loss is reducing after every epoch, and after 10th epoch it is reduced and almost stable. Okay, so when you get almost stable loss and almost stable accuracy, you can stop performing for more number of epochs. All right, now important part is now how to predict the model. So for that purpose we need to get confusion matrix. Okay, so confusion matrix is one of the important aspect using which you can predict and you can talk about the model, that how well your model is performing. That is a performance measurement matrix basically. Okay, so accuracy is not the only thing using which you can predict that how well your model is working. So here what we are doing is we are actually using the confusion matrix, and we obtain the confusion matrix. So here this confusion, you must be aware of confusion matrix. For binary classification, the confusion matrix will be 2 cross 2. So you will have this confusion matrix here, 251 can 19 281, and how to interpret it. Okay, so let us talk about interpretation of confusion matrix. Okay, and we obtain various measurement scores, performance matrix like accuracy, precision, recall, and F1 score. And let us talk about that, how to obtain and how to calculate. Although I have calculated it directly over here using code, but we can understand how to use it. Okay, so let us look at this particular thing. Okay, yeah, we perform all these operations, and this is what our model perform. This is how it perform. Okay, and you can see that training accuracy is above almost 84%, almost 85%, and testing is also a good one. Okay, similarly we are having less, we are reducing our able to reduce our loss. Yeah, now fitting and training the model. So finally the model is fit and trained for 15 epochs, and like this we did just now. Okay, let us talk about the this particular confusion matrix. Okay, in confusion matrix the result we obtain is, for example, for this particular model we obtain 156 78 5 385. Okay, remember this confusion matrix. Okay, now here what confusion matrix actually reveal. Okay, the first part is it reveal true positive, and the last part is true negative. Now, what do you mean by true positive and true negative? That means 156 are truly having malignant. Okay, they are malignant and truly identified as a malignant. Okay, and similarly 385 images were non-malignant and truly identified as a non-malignant. Okay, so TP is actually true positive. True positive stands for which was a malignant one and identified as a malignant, truly identified that okay, yes, it is malignant, okay, cancerous. And true negative means that means they were negative and truly identified that they are negative, that means they are not malignant. Okay, so this result shows true positive and true negative. But these two things are very important, the false positive and false negative. False positive means, okay, that it was not malignant, but it is identified as malignant. It was not malignant, but identified as a malignant. So that is a falsely identified as a positive. Okay. Similarly, that is known as a type 1 error. Positive is known as a type 1 error. Type 1 error means what? Assume that somebody is having not having malaria, and your laboratory result give that he is having malaria. Then what will happen? Doctor will start giving medication. So he'll start taking medicines. Is it clear? So similarly, COVID, if somebody is not positive and laboratory result shows that he is positive, then what will happen? The treatment will start. Okay, so that is a type 1 error. Okay, that is a dangerous thing, right? Because you are not having that symptom and it is giving you that you have that symptom. But this one is more dangerous, false negative. False negative means what? Okay, that means he is having a COVID, okay, and laboratory result says that he is not having COVID. Okay, false negative. What will happen? See, in this case, what happened at the most that he is not having COVID, but treatment is started. That is false positive, type 1 error. But this type 2 error is very dangerous. That means he is having a cancer, but detected as non-cancer. Then what will happen? Treatment will not start. Then there is a big risk against that particular person, isn't it? So false negative results, okay, having more false negative means your model is weak. Okay, although you are getting good true positive, true negative, accuracy is good, okay, it doesn't make sense, okay, unless you are controlling your false positive and false negative. This is very important, and this can be measured. This can this will be reflected using your precision and specificity and sensitivity. These three measures are very important. So from confusion matrix, okay, not just accuracy, but we obtain other parameter, other performance measurements, and using that you can identify how well your model is performing. So performance of model doesn't depend only on accuracy. Performance of model depend on your various other factors. Okay, performance matrix, performance measurements. Okay, so like here you have validation accuracy, that is fine. Okay, for this particular result, okay, here is a result. Okay, for this particular result, your performance valid accuracy is 82.24%. Okay, that's fine. But precision or and recall, okay, these are two important things. Okay, precision is also known as PPR, that is positive predictive value. That is important. It is a ratio of true positive to the sum of true positive and false positive, TP plus FP. That means how well your model is able to identify something which is malignant as a malignant, truly positive result it is providing. So here TP is around 82.88%. That means your model is yeah, able to detect that out of 100, 82.88% positive as a positive. Okay, so that is precision. Okay, whereas recall is actually like 82.33%, and recall we understand into next part. Now specificity, okay, sensitivity and recall are same. Okay, so we'll when we talk about sensitivity, I'll talk about that. Okay, Specificity is that it is represented as a ratio of true negative to sum of true negative and false positive. Okay, so sense specificity is again very important measure. So specificity says that like how good probability of correctly identifying the benign, that is non-malignant images. That means how good it is predicting that it is not cancerous, right? So that is a specificity. Sensitivity again is a important thing, very important part. So sensitivity says that okay, it measure to identify true positive over some of truly identified malignant and falsely rejecting malignants. Okay, this is the important thing. So in other word, it is TP divided by TP plus false negative. Okay, the less false negative are, TP is higher. Okay, and in our case sensitivity is 85.35%, doing well. Okay, uh, and finally F1 score. So F1 score is basically it is giving a harmonic mean between precision and recall. So you can see that how balanced your model is, whether it is going giving you a good balanced result or not. Okay, so it gives a trade-off between recall and precision. So here we got 82.06 F1 score. So it sounds good. That model is doing good. Finally, we talk about FDR, that is false discovery rate. So false discovery is actually lower the FDR shows how good the model is able to minimize the false positive. So FDR is actually 1 minus specificity, and like it is actually false discovery rate. False discovery rate found is 17.12%. Okay, that is 1 minus specificity. Then FNR, that is false negative rate. So false negative rate is ability of model to describe how good the model is able to minimize the false negative. Okay, and it is addressing to type 2 error. This FDR is addressing to type 1 error, and this FNR is addressing to type 2 error. So type 2 error is 14.65%. Okay, whereas type 1 error is 17.12%. Okay, so this is very important thing. Okay, and it all depend on how your specificity and sensitivity you are getting. Okay, the higher specificity and sensitivity you have, lower the type 1 error and type 2 errors are. Okay, so we have to control them. Okay, so basic purpose of model is now what to do. Okay, how to control them. So obviously, as I told you, that you have to tune your model. Okay, you have to tune your various parameters of the model. You can include more number of hidden layers. You can include change the convolution layer. You can obviously change the feature maps, size of feature maps, use different kernel, etc. So it is purely intuitive. With experience you can perform, and not with the single model. You have to develop and work on different models until you are getting optimum good results. Okay, and then you can compare these models, and then you can suggest the model which is providing the best possible results. Okay, so that was it. It was about all about our topic. Okay, so with this I would like to conclude. Okay, I hope the thing was clear to you. Okay, I was able to explain you in. Although see, it's a long topic, it's a very huge topic. A lot of things are there, codes and things. But at least you have a concept and idea that how this particular thing works, convolution neural network. All right, and with these examples and code, okay, I hope that I am able to answer you. All right, so if you need to if you have any query or question or anything, so we can have question session here. And same way like all right, and if you have any other query personally, you can mail me here. My mail ID is over here. You can obviously mail me. All right, so with this I would like to conclude. And yeah, any questions? So let us go to questions.
Sir, question is visible on.
Yeah, Dr.
Uh,
Sharma. uh,
Sir,
Sir
question is
Mithananda is
visible.
asking.
Well, is it
Question is like
okay?
CNN on .csv dataset is advisable or not?
Uh, is it available on chat? Where is it? Can you
Yes, yes,
tell me?
sir. It is available on the screen also. Can you
No,
see
I'm
the
not able to see that.
screen?
Okay, let me stop sharing my screen, right? So
Yes, yes.
that will be fine. Okay. CNN on .csv dataset is advisable or not? Okay, I tell you, this question is from Sarmister Nanda. Sarmister, CNN is basically for the purpose of training the images. So CSV contain the feature sets either in categorical manner or in form of numerical data. Okay, so that will be a physical data available with you. All right. Whereas CNN is actually a classifier which classify train the image in convolution layer. So your input will be image, not the CSV file, right? If you have CSV file and if you want to like you have feature set available in form of CSV file and you want to train, then you have to use artificial neural network, ANN. You have to develop only, not the CNN part. Okay. Saroja is asking which tool is best for image classification using convolution neural network, PyTorch, TensorFlow, Keras are all open source. And okay, yeah. See, which basically these are libraries. All right, the code which we are writing is using either Python or R or SAS, okay, whichever is or Julia is also available now. All right, but this TensorFlow and Keras, they are open source. Okay, they are open source libraries. TensorFlow contain excellent functions. Okay, using a single function you can perform lot many things. Okay, so Keras is working on top of TensorFlow. So Keras contain beautiful functions that we are using. Okay, they are open source, so you can use them. How to choose different layers? Yeah, different layer that depend on on, it's a purely intuitive work. You can start with single convolution layer initially with a single hidden layer. Then with you can increase number of hidden layer, check the output. Okay, if you are getting better accuracy, if you are going towards better accuracy, you can keep on increasing layers. You can add more nodes into layer. Okay, and you can perform. Okay, Priya is asking, instead of using defined activation function like ReLU, can we define customized activation functions? Yeah, you can do that. If you are good at uh, arranging your own activation functions and you have that control, you can definitely do that. Otherwise, we have wonderful activation functions ready with us. We can directly use them. Okay. Give the steps for setting this environment for GPU and Colab program. So we will execute. Okay, I'll show you. Okay, let me share the screen. We'll show you how to set the GPU. Okay, just give me a minute, right? Give me a minute. Okay, I'll share my screen again and show you how to do that. Okay. Wait a minute. Okay. We'll go to next question. It and I'll show you. Okay. I'll share the screen. We'll show you. It is very simple. Like you and you are using Colab. Okay. In Colab, you have runtime option available. Runtime option. Go to runtime option and select okay, CPU, GPU, or TPU, whatever you require. Okay. So you can select GPU from there. Can COVID-19 virus attack on directs? Actually, this is not relevant to our convolution neural network. This is actually a medical profession related question, basically. So I am not competent enough to answer this particular question. All right, because whether COVID-19 virus attack on skin or not is a medical field question. Okay, sorry, I cannot answer you this. Yeah. Anything else? Any more question? Yeah, Kanchan is asking, can CNN models help in disaster? Yeah, it obviously, even you can, the prediction, okay, the prediction, if you look at the windy.com, okay, they are giving the prediction. So how they are giving prediction? Prediction is purely based on this CNN model. Okay, they have data. Okay, they have data of every minute, okay, how the cyclone is moving. So based on that data and images they are capturing using Eurosat. Okay, they are using Eurosat images, satellite image, and those images they are using, and based on that they are predicting the direction of the cyclone. So you can definitely, yeah, even all this. Okay, what you are doing with all these satellite images? We are using satellite. ISRO is doing the same thing. They are using satellite images, and they use CNN models for the prediction purpose, for weather, for monsoon, everything. Okay, you can do that. Even images, and even water reservoirs, and a lot many things, jungle. Okay, whether it is increasing or decreasing of homeland, roads, etc., everything. Kindly send PDF file. Okay, I don't have any PDF, it is a
Okay.
PPT actually. All right.
Uh, Sir, enough.
Yeah,
Please
is it okay,
over
Pravisna?
to Madita madam. Okay, sir.
All
Over
right.
to Madita.
Yes, sir. Yes, that is also my question. How to set GPU on Colab, but no problem. We will
I'll
discuss
show you.
it.
Okay, I can show
Okay.
you. I just share the screen and show you. Just give me a
Okay,
minute.
no problem, sir. Please, just for a minute, please.
Should I continue or you want to end it?
Sir, as you wish.
Okay, I can share. No issue.
Hi, yes,
It's
sir.
a matter
Please.
of a minute. Yeah, it's a matter of a minute.
Yes, sir. Yes.
Okay, so fine. Can you see my screen?
Yes, it is in process.
Fine. All
Yes,
right.
sir.
So this is your Colab, right? So Colab, you have this option runtime, right? Runtime option. Runtime option. Simply click it. Okay. You have change runtime type here. Change runtime type. Click on that. So it will give you option here, hardware accelerator. So you can select your accelerator here. None. None is default CPU. If you select GPU, you have GPU. If you select TPU, you'll have TPU. But make sure that when you use TPU, select TPU, you will have limitation as far as the use of TPU is concerned. Okay, so they provide you for, because GPU and TPUs are shared by number of people at same time. Okay, so they don't want that you just occupy it and don't use it. All right, it is free, perfectly, absolutely free. So your code is executing directly on their server. Okay, on their GPUs. So you can select GPU and click on save. It's simple. So you have GPU now with you. Okay, and execute your code on GPU. All right, but even to process these 3000 images on GPU, it will take around 40 minutes. Okay, now imagine if, what if you are not using GPU? Okay, if you are using simple CPU, it will take 7 to 8 hours minimum for 3000 images. If it is more than that, 10,000, 11,000 images, you just uh, just keep it for training purpose and sleep and wake up early next in the morning, and by that time you will be able to. All right, is that okay?
Yes, sir. Thank you very much,
Yes.
sir.
All right, all right. I'll stop sharing now.
Okay.
Anything else you want to see?
Yes, sir.
Okay, all right.
Okay. Thank you. Really informative and practical session it was. Definitely, it will be beneficial for the people who actually working on the neural network and related test sets. So, moving further, I would like to request program convener Dr. Balkrishna Sharma to propose the vote of thanks. Over to BK sir.
Thank you, madam. Good afternoon to one and all. It's my privilege to propose a vote of thanks. Words are small for saying something for this distinguished personality. Their skills and vast knowledge will definitely enlighten and motivating to our students, and definitely in future they will get the support to catch their career goals. I also like to extend my gratitude and thanks to Vice Chancellor, Mandsaur University, Dr. Shailen Sharma, Dean Engineering, Dr. Pradeep Lakshkar, HOD of Department of Computer Science and Application, Dr. Nilesh Jain, and all the faculty member, staff who actually make efforts for the success. I also thankful to Praveen Bhargav sir, Mudita madam, who make and who contribute their efforts for the success of this workshop, and very thankful to all the participants without because without that this is not successful. I, on behalf of the Department of CSA, Mandsaur University, give the deep regards to you. Thank you, sir. Thank you to all of you. Thank you, sir.
Thank you very much, Dr. Sharma, Dr. Bhargav, and Professor Mudita. Thanks for everything, and thanks to all the participants. Have a
Thank
wonderful
you
day.
very much,
Take care.
sir. Sir, yes, it's a very
Thank you,
wonderful
sir.
and it's
Thank you,
very
sir. Thank you.
informative. Thank you, sir.
Thank you.
Thank you. Thanks.
Thank you. Thank you, sir.